Welcome to AI Paper Slot. Today we are looking at the paper Self-Evolving World Models for LLM Agent Planning. The researchers here tackle a massive problem in agentic AI, which is that world models, the things that predict future states of an environment to help an agent plan, they usually degrade the second the environment shifts. And updating their neural weights online is, well, it's computationally ruinous and causes catastrophic forgetting.
Right, it just destroys the model's baseline knowledge.
Exactly. So the paper introduces a training-free framework called WORLDEVOLVER. It freezes both the agent and the world model weights, but evolves the deployment time context. It does this using three things. First, episodic memory, which retrieves past text transitions based on action token Jacquard similarity. Second, semantic memory, which extracts reusable heuristic rules from prediction failures. And third, selective foresight, using token probability to gate confident predictions. The result is massive improvements in agent planning success rates on ALFWorld and ScienceWorld benchmarks without a single gradient update.
Yeah, it's really a profound shift in how we handle dynamic environments. The standard impulse in the industry right now is to just throw more compute at the problem, right? Try to force the model's internal parameterizations to adapt online.
Which never works out well.
No, it doesn't. But what this paper demonstrates is that you can effectively give an agent a self-curating dynamic scratch pad, one that gets smarter during the exact moment of deployment, completely sidestepping the nightmare of online fine-tuning.
Okay, let's unpack this, because to really understand why WORLDEVOLVER matters for anyone, listening to this who's building agents right now, we need to look at the baseline failure modes of LLM Foresight. Let's map out the standard setup. You have an agent policy, let's call it pi theta. Its job is to decide the action.
Right, the decision maker.
Yeah, and alongside it, you have a world model, W theta, which predicts the next observation to help the agent plan that next move. But the friction happens at the sim-to-real gap. It's like, think of a chess player who can think 5 moves ahead, but their mental board is missing a piece. If they act on a flawed simulation, they will blunder. If you leave your world model frozen, it just hallucinates when task instances shift.
Exactly. And, if you try to fix that by updating the neural weights via gradients online, the model breaks down entirely.
Right, because of catastrophic forgetting.
Yeah, catastrophic forgetting. When you perform gradient updates on an LLM based on immediate localized new observations, the backpropagation process over-optimizes for that specific new data point. It violently shifts the weights.
So it basically overwrites the broader representations it learned during pre-training.
Exactly. You might teach the model the new rules of how a door opens in this one specific room, but in the process, it completely forgets the general physics of, how to pick up an object. Right. The network basically gets amnesia for everything outside of the immediate feedback loop.
Okay, so the weights are absolutely off limits for online learning.
Yeah.
But when I read this, my immediate pushback was, why not just build a massive RAG pipeline? Like retrieval augmented generation. Yeah. Why not just use offline data sets of previous trajectories? That is what baseline models like ROMFI do. Why does the system need to evolve online?
What's fascinating here is that it comes down to ground truth accuracy versus, statistical generalization. Pre-computed offline trajectories dilute the specific localized dynamics of the actual environment the agent is currently deployed in.
Oh, I see. So it's too general.
Right. If your agent is navigating a specific kitchen in a text-based game, retrieving generalizations of 1,000 past kitchens doesn't help if this specific kitchen has a broken fridge, When an agent takes an action, the environment responds right then and there. That is a realized transition.
It records exactly what happens right now under these specific conditions.
Yes. And static offline retrieval just throws away that immediate golden data. We need the agent to learn from its immediate loop.
We have to exploit the immediate past. And since we can't touch the weights, we have to evolve the context window itself. Which brings us to the first pillar of this framework, episodic memory.
Correct. So episodic memory stores exact, concrete, realized transitions. It captures the previous observation, the exact action taken, and the resulting next observation.
And then it uses that to guide the next move, right?
Yeah. When your agent is drafting a new action, the system retrieves the top 5. So K equals 5 most similar past transitions to provide context.
Here's where it gets really interesting, though, because how they handle that retrieval is super technical. Normally, standard Ladry just uses full-state action text, right? You take a massive text block, embed it into a dense vector space, and run a cosine similarity search.
That is the intuitive approach, yeah. But it completely fails for text agents. Think about what a state description looks like in something like ALFWorld or ScienceWorld. It's like a massive block of text. You see a red apple on a wooden table next to a blue lamp and on and on.
Right, the descriptive fluff just drowns out the actual action signal.
Exactly. The system gets confused by the scenery. So WORLDEVOLVER throws out the dense embeddings entirely for this step. Instead, it calculates similarity using a Jacquard score, and it calculates it exclusively over the open vocabulary action token set.
Okay, let's unpack Jacquard similarity for anyone who hasn't used it recently. It's basically just a mathematical measure of overlap, right? Intersection over union.
Yeah, exactly. But the brilliant part is the constraint. It only looks at the exact word tokens of the action. If the proposed action is open the red fridge, and your past memory has an action that was open the blue fridge, the Jacquard calculation strips away all the background state descriptions. It just asks, how many of the exact same action-oriented tokens are we using?
So it's a much sharper tool. It zeroes in purely on the mechanical intent.
It is. And the hard data from the Word2World evaluations proves it. Using just this episodic retrieval boosted exact match prediction accuracy on the Gemma 426B backbone from a zero-shot baseline of 3.6% all the way up to 47.16%.
Wait, really? From 3.6 to 47%? That is a massive jump without a single gradient update.
It's huge. It proves that the world model doesn't need to be retrained. It just needs a noise-free context window of what actually happens when an action is triggered.
Okay, so episodic memory handles exploitation repeating known actions. But what if the agent tries something new? It has to explore eventually, and when it does, the world model is probably going to predict it wrong. How do we turn those failures into rules? That transitions us to semantic memory.
Right. Semantic memory is all about learning from mismatches. When the predicted observation doesn't match the actual observation, the system needs to compare them. But it can't just do a naive string match because, the door is open and you have opened the door, mean the same thing but look different.
So how does it actually compare them programmatically?
It uses a mapping function that factorizes the raw text into structured tuples.
Like breaking it down into fridge 1 is open, that kind of...
Exactly. It forces the text into rigid tuples, then it compares the predicted tuples against the actual observed tuples, and if there's a mismatch, an LLM critic generates a textual heuristic rule based on that failure.
Okay, I have to throw a massive red flag here. Because isn't it incredibly dangerous to let an LLM write its own rules based on a single mismatch? I mean, what if the LLM critic hallucinates a bad rule and permanently poisons the memory? Like it decides dropping an apple makes it float and embeds that into the context.
You'd be entirely right if the system just accepted those rules blindly. But this is exactly why the evidence score exists. It acts as a continuous validation check.
How does the evidence score work? Is it just a running tally?
Basically, yeah. When a rule is generated, it gets an initial evidence score denoted as E of 1. As the agent keeps interacting, it doesn't just trust the LLM critic. It verifies the rule against the subsequent factorized tuples.
Ah, so it builds persistent frame axioms safely.
Right. If future observations support the rule, the score goes up by 1 over the total size of the semantic memory bank. If they contradict, it goes down. And crucially, only rules with an evidence score strictly greater than 0 stay in the context window.
I love that. It's a living confidence metric. But, even with episodic and semantic memory, sometimes the world model is just guessing. It's venturing into the complete unknown. How do we prevent bad foresight from sabotaging the agent? Because prior work, like the ITPI baseline, actually underperformed a no-world model baseline because the agent was misled by confident hallucinations. Right.
Exactly. If the world model feeds the policy a highly detailed but deeply flawed simulation, the policy optimizes for a reality that doesn't exist. It'll walk straight off a cliff because the world model promised there was a bridge.
So what does this all mean for WORLDEVOLVER? It uses selective foresight, right, which is basically the art of abstention. It's like having a usually brilliant co-pilot who occasionally gets disoriented if they sound even slightly hesitant on the comms. You just mute their mic and fly visual.
That's a great way to put it. WORLDEVOLVER calculates a normalized confidence score based on the geometric mean token probability.
Walk us through that. What is geometric mean token probability?
When an LLM generates a prediction, it assigns a probability to every single token it outputs. The system takes the probabilities of all those tokens, multiplies them together, and takes the nth root. It's a mathematically robust way to measure how confident the model is in its own generated sequence as a whole.
And if that confidence is below a specific threshold, say tau is 1 minus 10 to the negative 4, the agent is given an empty set, right? Like zero foresight at all.
Exactly. The prediction is thrown out. If we connect this to the bigger picture, this abstention mechanism completely rescues the agent. Filtering out low-confidence predictions lifted the Gemma 426B A4B reflect agent success rate on ALFWorld from 24.63% to 27.61%.
And that's huge because the baseline agent with no foresight was at 26.12%. So without selective foresight, the hallucinating world model was actively dragging performance down.
Right, it's the ultimate guardrail. Knowing when not to predict is arguably more important than predicting accurately.
Okay, so we have the architecture. Let's look at how this entirely training-free stack performs in the wild across different agents and models. We evaluated on two distinct agent types, react and reflect. And across models like Gemma 426B, Qwen 3.59B, and even GPT 5.4 Mini. But the continual learning proof in Figure 4 is what really stood out to me.
Oh, absolutely. The success rate actually scales up as the trial index increases from 1 to 5.
Because the Marybanks compound, the model literally gets smarter during deployment.
Exactly. And people usually worry about latency with these complex compounding memory systems, but the efficiency here is incredible. The compute tax is negligible. The runtime only goes from 1.05 seconds per transition for zero shot to 1.48 seconds for WORLDEVOLVER.
Less than half a second of latency for a self-correcting world model. And looking at the task breakdown in Figures 9 and 10, there are massive gains on ScienceWorld tasks that require tracking environment dynamics, like thermodynamics and lifespan tracking, though state change tasks remain near zero.
Yeah, likely because the transitions in pure state change tasks are too sparse to be reliably abstracted into rules. But wherever the environment possesses trackable physics, the memory architecture captures it beautifully.
I noticed an interesting quirk in the data, actually. Weaker or smaller models, like the Gemma 26B, they actually get a bigger boost from selective foresight than powerhouse models like GPT 5.4 Mini. Why is that?
This raises an important question about inherent capabilities. When task difficulty is hard on ALFWorld, GPT 5.4 Mini is already operating near its ceiling. It guesses accurately most of the time, so foresight offers marginal gains.
Because weaker planners leave more room for useful world model guidance.
Exactly. The Gemma models desperately need the explicit guardrails of the memory context. It proves WORLDEVOLVER is an incredible equalizer for mid-tier open-weight models.
Which really brings us to the core takeaway for you, the listener. If you are building ML agents for production, you don't need to burn GPU cycles fine-tuning world models online just so your agents can adapt. We know that causes catastrophic forgetting.
And it's economically unviable at scale. Evolving the non-parametric memory context is cheaper, safer, and highly effective. Combining action token Jacquard retrieval with confidence gating is an architecture you can implement today.
I want to leave you with one final provocative thought. We just talked about semantic memory, how it uses factorized text tuples to generate persistent heuristic rules from prediction failures. Could we deploy this exact semantic memory architecture into entirely alien, synthetic, or encrypted data environments?
That is the logical extreme of this framework, and it's thrilling.
Right. Could we unleash a frozen LLM to reverse engineer the fundamental laws of physics of a completely unknown system, using only text and its own mistakes? An automated scientist mapping an alien world, one Jacquard similarity score at a time. Until next time.